next speaker is Jonas Hannestad. Please tell us something about PGC-1 Alpha, I think. Very exciting stuff.
All right. So good afternoon, and thanks to the organizers for giving me the opportunity to speak here today. I'm with a company in the San Francisco Bay Area called Tranquis Therapeutics, and our primary focus is neurodegeneration. And the underlying hypothesis is that microglia and other myeloid cells play a role in disease progression in diseases like ALS, frontotemporal dementia, Parkinson's, Alzheimer's, etc. And the way we modulate myeloid cells and microglia is through PGC-1 Alpha, which I'll talk about in a second. But what we found is that when you upregulate PGC-1 Alpha, you modulate cell energy metabolism in these cells, and you inhibit their inflammatory state. And we think that is beneficial in these diseases. And we have a pipeline of compounds that do this, and our lead compound, TQS-168, just completed phase 1 and is now ready for a phase 2 study, which we're planning to start next year. But that neurodegeneration focus is not the reason I'm here today, or not primarily at least. The reason I'm here today is because we have some, what we believe is compelling data in aging in mice, and I would like to get this audience input on that. Because for me, aging is a new field. I've worked in neurodegeneration for 25 years, but not in aging specifically, and it's also a field that our company is not very familiar with. So I'm looking forward to input on the data that I'm about to present. Brief background on PGC-1 Alpha. So PGC-1 Alpha is a transcriptional co-activator that's present in all cells, and it has a multitude of effects, but some of the most important ones are mitochondrial biogenesis and mitophagy, or mitochondrial quality control, and also metabolism, such as fatty acid oxidation, glucose metabolism, etc. So those are obviously, mitochondria and metabolism are obviously important processes in aging. So in theory, you would think that modulating PGC-1 Alpha could be beneficial in aging. But in our focus on neurodegeneration, we have some actual data to support that. So first of all, we know that our molecules increase PGC-1 Alpha gene expression in vitro, and we focus, as I said, mostly on myeloid cells, because that's our underlying hypothesis. So here are just some examples of the data that we have. It increases PGC-1 Alpha gene expression in mouse microglia, in human blood, white blood cells, and it also increases mitochondrial mass, which is a key role of PGC-1 Alpha. Then we've tested this molecule in many models of neurodegeneration, mostly ALS and Parkinson's. And while the primary focus of those animal model experiments was to look at disease phenotypes, on which the compound has beneficial effects, and also the underlying biology, especially the myeloid cell biology, what we did see in these experiments is that TQS-168 increases lifespan. So we wondered, well, this could be just related to the, sort of the neurodegeneration transgene that's present in these mice, but it could also be a broader effect on longevity. Therefore, we designed this experiment to actually look at not so much longevity, but health span in mice. We took 2 groups of mice, so these are wild-type black sex, young mice, 3 months old, and old mice, 18 months old. And we chose 18 months because this is I guess it maps onto human age. It's approximately 60 or so. So we thought that would be an age that you can translate to humans. Because as was mentioned, I think yesterday and the day before several times, that in the case of metformin, it's not something you want to start in young people, right? Unless they're diabetic, obviously. But it's something that you want to start later in life to slow aging. And this is the way we're thinking about our compound as well. So in the study, we dosed the mice for 4 months, and we did various in-life assessments during that time, which I'll talk about today. At the end of the 4 months, we took down about half of the mice And those tissues are currently being processed for transcriptomics, and I don't have those data today, unfortunately. But then there's a separate cohort of mice that is being dosed still, and they'll probably be dosed until at least the end of the year, and that's a cohort to look at lifespan. So what did we find in these mice that were dosed for 4 months? So one thing we looked at was this Frailty index, which has been presented several times both today and yesterday. So I think and this audience is probably familiar with this scale. But what we found was that at baseline, first of all, 18-month-old mice score higher than young mice, as would be expected. And over the course of 4 months, the young mice don't develop any frailty to speak of, whereas the 18-month-old mice, by the time they're 22 months old, they have much higher frailty scores. However, in the TQS-168 treated mice, that score is reduced by about 50% at the end. So again, I'm not familiar with the aging field, but if this kind of effect size in neurodegeneration would be considered very large. So I'm curious to input on these data specifically. And when you look at the specific parameters that are scored in this with this index, you see that this is not an effect on any specific organ or system. It's across a variety of organs and systems. And the other thing I want to point out is that while we've focused mostly on myeloid cell biology and the effect of this compound in immune cells, it's difficult to imagine that all of these effects are due to effects on immune cells. So presumably, the compound increases PGC-1 alpha in a variety of other tissues, which we have yet to confirm. At the beginning of the experiment, we randomized, or we distributed the mice so that their body weight was matched, because body weight was an important parameter we wanted to look at. And as is well known, the old mice weigh more than young mice. And at the end of the 4 months, the young mice didn't change much in weight. The old mice that were treated with TQS-168 lost about 30% body weight on average. And losing body weight can be good, but it could also be bad in older subjects, as you know. So we used echo MRI to measure what did they lose. And all of the loss was fat. So the lean mass stayed constant. So presumably they preserved muscle mass and they lost fat mass. We didn't look at bone specifically, but that's another important parameter, obviously. And then grip strength is another parameter that decreases with aging in mice. And as you can see here, old mice have about 50% less grip strength than young mice. And after treatment for 4 months, the young mice regained grip strength to a level that was similar to young mice. And this is displayed here both as absolute grip strength in grams, and then the percent change from baseline in individual mice. And as you can see, in the treated group, almost all the mice increased in grip strength over those 4 months. Then the last in-life assessment we did was treadmill endurance. So we basically trained the mice to run on a treadmill until exhaustion. And in the young mice, there was at least no significant effect. It appears that there may be a slight increase here in endurance in the TQS-168 treated young mice. But in old mice, we definitely saw an increase in endurance. And this is measured both as the distance traveled and the time until exhaustion. So in summary, we've shown that TQS-168, which is a small molecule PGC-1 alpha enhancer, can reduce frailty and body weight and fat mass specifically in 18-month-old or 22-month-old mice, and it increases grip strength and treadmill endurance. And the data that we don't have yet, which will be very informative, I suspect, is bulk transcriptomics with RNA-seq in muscle, fat, and liver tissue, and then single-cell RNA-seq in brain tissue, because we are still very interested in looking at microglia and neurons with our focus on neurodegeneration. So as I said before, we have this compound is phase 2 ready, and it will likely go into a proof of concept study in ALS next year. But what I would like feedback on from this audience, and hopefully in conversations later today and tomorrow, is what does a proof of concept study in older humans look like? What disease or what specific parameters would you measure? So that's what I'm hoping to take back from this meeting. So I want to thank my colleagues at Tranquis, and specifically Rohini, who was supposed to present here today. Unfortunately, she couldn't make it. Thanks to Dan Weiner, who's a collaborator at the Buck Institute, and also our collaborators at WuXi. Thanks for your time.
Thank you so much for a great talk. We have a question. So.
Thank you for the very interesting talk. So, but that was a very drastic loss in body weight. You might even consider going into obesity. No, but as a mouse aging researcher, I wonder, are you considering adding maybe like a weight-matched control or a lower dose? Because it might be due to caloric restriction, the improvement in frailty, right? Yeah, so I think there are many caveats. Yeah, the point on obesity is something that we're also potentially interested in. I mean, I think there are many caveats, because I think it was Eric Verdun who mentioned that yesterday, that these are mice that sit in the cage, they don't have treadmills, they have unlimited access to food. So how does that translate to a human situation where you can't control food intake or activity, right? So I think that's one confound. But there's something we want to explore further, especially with the transcriptomics in adipose tissue, to really understand what is the effect of the compound.
Actually, I want to ask a question. So maybe I missed it. Did you look at UCPs in this? Because PGC-1 family was first discovered as regulators of UCPs, and that might regulate enzyme metabolism, right?
We haven't yet. So we're planning to do. So we've taken muscle tissue, and we are planning to do some mitochondrial assays in that.
All right. Yeah. Great. One more question.
That is very exciting. I think part of the success is kind of what you said. You have to do it in old models. In fact, and I'll be happy to give you some views later on, but my question is, the PGC-1 Alpha was a target by many drug companies before. It failed, if I remember, on safety issues. Can you tell me why, and how did you overlook it? And did you have an ALS model? Did you show us an ALS model results here?
Yeah, very briefly.
Okay.
So we have multiple experiments in the SOD1 model, but that's for a different time. So so I think that the earlier PGC-1 alpha compounds were probably not as specific, so they had off-target effects, is my guess. But what we've seen is that both in the toxicology studies up to 3 months of duration, the only adverse effect we see in both the rodent and the non-rodent species is some slowing of weight gain. So we see no adverse events or adverse effects in tox species. And then in phase 1, in healthy volunteers, dosing up to 7 days at the dose levels that we want to get to, the adverse events were all mild, and we saw no changes in clinical labs, ECG, vital signs, etc. So, phase 1 already? Yes, we've completed phase 1.
Super exciting. Thank you so much.